Hello and welcome everyone to our 23rd FAIRWork webinar, today with a focus on decision-making and orchestration with multi-agent systems. So a short reminder of the FAIRWork project. For those who don't know, if you want to have details, we have other webinars going into details and explaining additional stuff. Just visit our website. But for now, it's one of the main focus of our project is the design of the democratic AI-based decision support system. So a decision support system which can handle complex situations with also considering the humans involved, not only the decision makers, but also the people involved from this decision. So for example, the workers in a working plant, that their needs also are considered. And our colleagues from Moa Colab, Gustavo and Rui will today introduce us how we use agents and multi-agent systems to support this on two levels. One for the decision making itself. So how can we come to a decision or a succession for a decision using these multi-agent systems, and on the other hand, the orchestration of the DIDSS, so of our decision support system, meaning that we have different AI services tackling different problems, and we use multi-agent systems to orchestrate the different services so that they fit to the concrete decision scenario, so that we can have this flexibility and adaptability of our whole system. And these are the two main focus of today's presentation. And without further ado, I hand over to Gustavo, who starts the presentation.
Thank
Gustavo,
you,
the stage is
Christian.
yours.
Thank you very much. Thank you. Good afternoon. So my name is Gustavo Vieira, and today I'm going to present with my colleague Rui Fernandes the webinar Decision Making and Orchestration with Multi-Agent Systems developed in the FAIRWork project. And as Christian just said, I'd like to bring attention to the previous webinars available on our YouTube channel, from which you can follow the progress and the evolution we've made. Welcome, everyone. So I'd like to start highlighting some important topics for this webinar, and with the question, why multi-agent systems? Multi-agent systems improve decision-making through decentralizing and representing stakeholders with their agentification. We develop a system that represents stakeholders in a decision-making process and their interactions to achieve the desired goal for the industrial application, which we'll present ahead. From Industry 4.0 to 5.0, the evolution into human-centric ecosystems which use human data in the decision workflow is tremendously empowering to the agent system. Such data embedded in the agents make the system oriented to the human reality and needs, as you will see. Ethics and human factors at the core. Aligned ethical criteria with real-world human data turns mass reasoning into a responsible decision support system. Ethics plays an important role in providing a system that is responsible regarding not only how the process develops, but also at the decision outcome reached. Having a system that not only uses human data, but that also reflects about the outcome reached in an ethical perspective is important for an accountable human responsible DSS. Mass-based work allocation use case. We have an interesting use case in which we are interested in allocating workers to production lines while balancing human needs with the production requirements and demands, matching these profiles. So in this slide, just as I said, to model human fairness in mass, we use human data to assist the decision-making process involving ethical aspects. Fairness in social dynamics, ethics embedded in mass supports fairness in decision-making with important social dynamics. One of the objectives of the system is to balance collective welfare with individual welfare. It's important to have a mechanism for conflict resolution when the individual welfare clashes with the collective. Alignment with societal values. It means that the purpose of developing fairness in the system is to align the decision-making process with the social values of the context. The same goes for the following: toward human-aligned decision support, where the multi-agent system is modeled to be aligned with these human values that we are interested in the context. We have developed for an industrial scenario a multi-agent system that recommends allocation of workers to production lines. These agents represent production line demands and workers' interests, which happens based on resilience and preference metrics originated from the human factors data. A conflict resolution strategy takes place to provide a more rich, informed decision-taking, which is based on job rotation and worker experience. So it was an allocation based only on performance and worker preferences yet. In the image, one can see a pool of workers from which they are selected and therefore allocated in the production line. But now we have an upgrade of this view. Then we have the watchdog mechanism. The watchdog mechanism was developed to give an increased and needed added value to this type of resource allocation. It addresses pertinent ethical concerns in the decision-making process and enables better informed decision-making, resulting in fairer and more democratic decision processes. So it happens basically in two main steps. When the decision maker triggers the system to recommend an allocation to a production line, the system accesses the available workers and starts a negotiation process, taking basis on resilience and preference parameters as it was in the beginning. Based on that, the workers are ranked following a score system. With that, the decision maker has a recommendation to allocate workers based on their performance level, translated as their resilience score and preference on being allocated to that specific line. However, this first negotiation doesn't consider the ethical sphere of the decision process. In this case, we are interested in having an equitable demographic allocation, considering at least half of the workers as females and also an average age under 35 due to the load demands of this type of work. This criteria can be adjusted based on the needs of the scenario. Then after this first negotiation round, the watchdog monitors what is the outcome and whether it trespasses any threshold defined in the ethical criteria. If it does, the ethical watchdog raises an alarm to the decision maker and alerts the fact. The decision maker takes the watchdog output and can then choose to trigger another negotiation round, considering all the most relevant workers from the previous round. This new round takes these workers and rearrange their position in the rank, while enforcing the ethical criteria established for the use case. As long as there are available workers that fulfill the ethical requirements, we expect to have a recommendation of worker allocation that addresses the ethical issues. So the idea is that the watchdog assists the decision maker to align with the criteria of that process. The system provides a series of relevant parameters to be considered when making the decision. In the first negotiation round, it checks ethical aspects, while in the second, it renegotiates worker allocation, enforcing the ethical criteria. A view of that mechanism interface can be seen in this slide, which I will show running soon. We have these production line requirements requiring 6 to 4 workers to be allocated, as one can see in the columns. The two rows represent each negotiation round. And now, with this video, I'll show this mechanism running of the ethical watchdog. So basically, it starts with the triggering of this line where you want workers being allocated to. We have this drop-down menu. Here we are selecting line 17, and you can see that the criteria for age and gender are not satisfied. So the decision maker chose to trigger a renegotiation and then consider this criteria being incorporated into this first negotiation round, which is solely based on performance, basically. And then we are waiting now for the second negotiation. And then it comes, and we can see that both criteria were satisfied. And then the decision maker can move on to the next line and ask again, using this example, we are using the drop-down menu to select the line 18 and see what is this first result of this the first negotiation. And we can see here that the criteria of age is not satisfied, so the decision maker can move on to another line, or he can address this ethical issue, triggering the renegotiation process. And with that, the multi-agent system now is computing, is incorporating the ethical criteria. And then we have another set of workers taking basis on this first negotiation round and being then incorporated in our result. And then for the line 20, we need only for workers, and then the result is they are also incorporating the ethical criteria for age and gender for this use case. So with that, I'd like to close this part going through a brief outlook. So we have mass empowered with human factors, where highly relevant data from stakeholders in the decision-making process offers the possibility of recommending resource allocation more fairly, taking into account the often counterpoint of production demands and human well-being. The data gathered from the workers and embedded in the agent system is essential for recommending worker allocations centered in the human. Societal aspects addressed through ethics. We have criteria aligned with human values embedded in the multi-agent system, allowing important ethical and therefore social issues to be addressed. The ethical watchdog agent that acts to monitor the ethical aspects relevant to the industrial use case in order to offer ethical decision support in line with human values, which therefore enable the decision maker to make a well-informed decision. And fairness as a process, focusing on continuous monitoring of outcomes to detect and correct ethical diversions, allowing equitable treatment to the stakeholders. So thank you very much for your attention. With that, I'll pass the word to my colleague Rui Fernandes to present the next part. Thank you.
Thank you, Gustav. Let me just share my screen. Are you already seeing the presentation?
Yes.
Okay, so I will speak about the orchestrator. Let me just move this a little bit. Okay. The orchestration software is a framework that revolves around the coordination and management of multiple software components, services, and tasks to achieve specific goals and objectives. The orchestrator was built in a modular approach, as can be seen in the figure. In this approach, the orchestrator element is the core component, and it exposes a secure RESTful API. When a request is sent to this API to acquire the available microservices outputs, it triggers the creation of two distinct types of agents, a microservice agent and a data collector agent. Microservice agents are dynamically created based on the number of microservices identified in the REST request. And each agents connects with a single microservice, considering that microservice requirements, gathering its output. These agents work autonomously, they run concurrently, ensuring that they operate independently, thus optimizing efficiency. The data collector agent is responsible for collecting and merging the data acquired by the currently active microservice agents to create and return the final output. This approach makes the orchestrator secure and easily scalable to include more scenarios and its corresponding microservices, and allows an implementation of decentralized orchestration of the available microservices. So looking into the operationality side of the orchestrator, let's simulate a request that sets the usage of 3 microservices of the workload balance scenario. So a request is sent. In this request, the microservices are identified. This implies the creation of these 3 microservice agents, 1 per microservice. Each microservice will then deal with the data preparation to obey the requirements of the corresponding microservice API. They prepare the data, they query the knowledge base, they construct the structure that they are required to construct, and they send the request to the microservices. Of course, that different microservices, different algorithms, we have here different computation times, so they may arrive at different times in the orchestrator. Upon the arrival of the last result, then we have the data collector agent working. It collects the data retrieved for all present active microservice agents and merges it into a single unit that follows the data model agreed upon for the data representation and identifies, of course, the corresponding microservice the data belongs to. And this data is then returned. So for the production planning scenario, the last one that was taken into consideration, the microservices can be very demanding, computationally speaking, implying long time intervals until a response is ready from the microservice. There's a different approach was also used on the implementation of the orchestrator. This approach still possesses the same type of multi-agents, the microservices and the data collector agents. However, they are now controlled through tasks. Due to the number of different services and the data that they require, the structure of the request was also modified. So the request now includes an Excel file with the other data, and this Excel file follows the template that is presented here on the slide, on the top of the slide. So we have the order, the due date, the priority, the geometries related to the orders, the quantity, and the molds. And we also have a set of parameters to basically define the context in which we are requiring the services to work on. So the start date and the days to plan basically set the time interval in which we want to make the data analysis. We also have the availability of the workers. Then to define the services we want to use or to get the results from for the production planning. We have these scenarios in a two-step approach developed by RWTH. And the first step is the order-to-line allocation, in which there are three different possibilities for the implementation of the service. And the second step is the worker-to-line allocation, in which there are three different services: the constraint programming, the reinforcement learning, and the Monte Carlo research, and as well as four different variations in terms of the optimization. A balance in which all variables are given the same level of priority, or a priority can be given for the worker's experience, or the worker's resilience, or even the worker's preference. But this means that we have, if we combine these two steps, we have 3 times 3 times 4, so we have a total of 36 possible services that we can use here on the context of this part. So we can do it single service, so we can select only a single service, or we can select all possible optimization variations for a method. So we have these different possibilities, which also means that we can have only a single microservice agent, or as before, multiple microservice agents working at the same time. And the idea here now is the following. So we have now the post request that arrives at Orchestrator with the information that we saw on the previous slides. And this allows the orchestrator to create a task and associate it with this request. Upon task creation, the corresponding microservices agents are generated. And we are also in the condition to provide the task ID to the original requester. At the same time, we have the exact same type of functioning. So we have the microservice agent or agents to query the knowledge database based on the information that we received on the order data on the Excel file, to prepare the necessary data to provide that data to the different microservices. The microservices run their algorithms, they provide us our data, and they return a response. Same thing, if we have a single microservice agent, okay, then it's just to pass that output or the data collector only needs to grab that result. If we have all four different optimization approaches, then the same thing as before. The data collector agent waits that all four results are available and merges it into a single response. The difference is now that that response is now attributed to the task. So multiple tasks can be created, they can run concurrently, but what I just described on this slide happens when we are looking into the operation from the orchestrator perspective. If we take the point of view of the original requester, after receiving the task ID almost at the beginning of this process, we are then in a situation in which we can query the orchestrator for the results. So a request is sent to the task endpoint, and a response is then given by the task. And here we can have two possibilities. So the first one, since the algorithms are time-consuming, maybe the algorithm still did not have enough time to run, so we still do not have any result. So we return that, okay, this task is still pending. If enough time has already passed and the algorithm has already run, it already gave the result back to the orchestrator, and the orchestrator already has that result on the task or associated with the task, then the response will be the result of the service or the services. And we have these two different type of implementations in terms of the microservices that were developed within the framework project. Thank you.
So thank you to Gustavo and Rui for this interesting presentation. And now we have time for questions. Are there any questions from the participants? Anything unclear, anything that should be explained in more detail, or also some input from our webinar participants?
If I may, I would have a question.
Sure.
So I was wondering, how did you actually create those agents? Do they have some sort of proprietary code, or did you define them on something like OpenAI or some other, agentic, some other platform that supports agentic AI?
No. We look into this, and the first approach was or the first idea was to use an agentic platform. However, given the context in which we are here doing the implementation, for instance, the type of communication these agents have, they do not need to I'm sorry, I'm missing the word. They do not need to exchange messages between them, because I can make the communication between this type of agents for this application through indirect communication. So based on shared data structures and good synchronization between them. So we went through a more simple approach. So what we have here is basically each agent runs on its own thread so that it can run concurrently. And we do the communication between agents, just like I have said, through indirect communication.
Thank you.
And complementing just the question for the negotiation process that I referred in the first part of the presentation, the agents are developed in the Jade platform. It's a Java agent development framework. In case you're interested, you can also check that on the previous webinars where we present the agents development. We refer to this framework there.
Thank you.
You're welcome. Any other question? Anyone?
Then thank you very much for joining the webinar. The next one will be on the implementation side more generally. So the IDSS, so a whole democratic AI-based decision support system and its different components and how they work together. It will be at the end of May or the beginning of June. We'll still have to make out the concrete date, but if you follow us on LinkedIn, we keep you posted. And thank you very much. Have a nice day, have a nice weekend, and see you next time.